Get ready for a journey into the pulsating core of nuclear power plants, those colossi of modern engineering that show us the most powerful and efficient form of energy at our disposal. However, as with any monumental technological advance, nuclear power plants bring with them complex issues and unusual challenges. Chief among them is the enigma of nuclear waste, this dangerous and radioactive byproduct that persists in releasing its harmful radiation for millennia, far beyond human comprehension. Faced with this perennial dilemma, a provocative and somewhat audacious question arises. Why don't we consider the possibility of simply catapulting this nuclear waste towards the sun? At first glance, this proposal might sound like a definitive and elegant solution to the problem of storing radioactive waste. After all, what could be more effective than sending our most dangerous waste to be consumed by the sun's nuclear furnace? However, as we delve deeper into this question, we discover that the answer has scientific, technical, and even philosophical complexities. This debate leads us to ponder the limits of human innovation, the ethical responsibilities that accompany technological progress, and the implications of dealing with forces of nature that could ultimately define the future of our planet and humanity. So let's unravel together the mysteries surrounding this intriguing idea and explore the potential and dangers it represents. At first glance, the solution to the nuclear waste dilemma may seem simple, almost obvious, but it's not that simple. The truth is that rockets can fail, they can explode, and when they do, the consequences are undoubtedly catastrophic. So imagine this scenario. A rocket designed to transport our dangerous nuclear waste, destined to be launched far from Earth, ends up failing during its upward journey. What would be the result? A scattering of radioactive material across a vast expanse of sky, generating a shower of contamination on Earth. The scenario is like something out of a horror movie, where the invisible threat of radioactive material spreads silently, contaminating everything it touches, without distinction. But here comes the curiosity. Even with an impressive launch success rate, such as that of the Falcon Heavy rocket, which boasts more than 98% success in more than 1,500 launches, that 2% chance of failure makes us rethink. After all, nobody wants to be responsible for creating a new Chernobyl, right? And if your mind was already racing at the thought of the complexity of sending nuclear waste into space, get ready, because physics comes into play to add extra spice to this already intricate discussion. Reaching the sun is a surprisingly more challenging endeavor than simply wandering off into space and leaving the solar system behind. Counterintuitive? Undoubtedly. But here's why. To make a direct trip to the sun, we would need an extremely complex space maneuver, which basically involves braking our orbital velocity relative to it. We're talking about drastically reducing our speed, which is nothing short of monumental, considering that the Earth is traveling around the sun at an average speed of approximately 66,487 miles per hour, or about 18.51 miles per second. Now, imagine the challenge. We would need an astronomical amount of fuel and energy to counterbalance this speed and then allow the sun's gravity to do the rest of the work, pulling us in. The problem is that this operation isn't just difficult, it's a real logistical and energy nightmare. And as you digest this information, it becomes clear that the journey to solving the nuclear waste problem is fraught with challenges that go far beyond the simple act of throwing it away. So, faced with the nuclear waste dilemma, what exactly can we do? The issue leaves us with two main choices, each bringing its own set of challenges and considerations. On the one hand, we have the option of storing this highly radioactive material in secure facilities, a kind of long-term quarantine, waiting patiently until the radioactivity drops to levels we can consider safe. On the other hand, there is the more innovative and somewhat futuristic option of nuclear recycling. This alternative, already explored by pioneering nuclear energy nations such as France and Japan, presents itself as a possibility, promising not only to mitigate the accumulation of waste, but also to turn it back into valuable resources. Recycling nuclear waste, however, is not so simple. The most complicated issue is undoubtedly plutonium. This element, a byproduct of recycling, is a double-edged sword. On the one hand, it has the potential to be an option for generating more nuclear energy, practically feeding the energy cycle again. On the other hand, it carries with it the sinister shadow of its use in the manufacture of nuclear weapons, a risk to world security. Now it's time to shed some light on one of the most emblematic and misleading issues in the world of science fiction: that neon green, bubbling liquid, often portrayed as the beating heart of nuclear power plants. The truth, my friends, is far less cinematic, but no less fascinating. The real protagonist here is a discreet but powerful hero. Solid ceramic pellets, small but formidable, which fit precisely into metal tubes. These pellets are an ingeniously calculated mixture of uranium-238 and uranium-235. All uranium has 92 protons, which identifies it as uranium in the periodic table. But what varies is the number of neutrons, which are particles in the nucleus of the atom. Uranium-235 has 143 neutrons, and uranium-238 has 146. In nature, most uranium is type 238, but for our power plants, uranium-235 is the most important, even though it is only present in around 4.5% of the mixture. When it receives a little push in the form of a neutron, it splits into two pieces, releasing a large amount of energy. This process is called nuclear fission. After fission, uranium-235 is transformed into other smaller elements, such as cesium, iodine, and strontium, which are called fission products. And although uranium-238 doesn't split so easily, it can capture a neutron and turn into uranium-239, which then becomes plutonium-239, another material that can be used as fuel or, unfortunately, in nuclear weapons. Over time, after about 6 years of use in a reactor, the amount of uranium-235 becomes so small that the fuel is no longer efficient. What remains is a mixture that still contains a lot of uranium-238, some plutonium-239, some uranium-235, and the fission products. This mixture is what we call nuclear waste. When these pellets, which are precisely housed in metal tubes, are bombarded by neutrons, they start a spectacularly powerful chain reaction known as nuclear fission. This process not only splits atoms in half, but also releases energy so immense that it can light up entire cities. We're talking about a force capable of feeding our modern society's voracious demand for energy, all hidden inside small metal cylinders that could go unnoticed in any corner of a laboratory. So, when we talk about nuclear waste, we're referring to a combination of fission products, still reactive uranium, and other radioactive elements. Once used, this fuel is initially stored in cooling pools, protected by water, which acts both as a coolant and as a shield against radiation. After a few years, when the radioactivity decreases a little, the waste can be moved into concrete containers, designed to hold it for up to 300 years. But as some radioactive materials last much longer, we are looking at long-term solutions, such as storing them in mountains to ensure they are safe for thousands of years. In short, dealing with nuclear waste is a big challenge, but it's important to remember that nuclear power plants, despite their waste, are a much cleaner source of energy compared to other forms, such as burning coal. What about the future of this waste? Some proposals include storing it in secure underground facilities, such as mountains, where it can remain isolated for thousands of years. Finland is at the forefront of this approach, with projects for deep geological repositories designed to seal nuclear waste away from humanity's reach and memory. When we compare the amount of nuclear waste produced with other types of waste, such as the toxic waste generated by coal-fired power plants, we realize that although the challenge of nuclear waste is significant, it is manageable, especially if we consider the alternatives of recycling and safe storage. We hope with great anticipation that in the near future, we will be able to celebrate the dual achievement of pure, revolutionary energy that lights up our lives without leaving toxic traces in its path. What do you think can be done with the toxic waste from nuclear power plants? Thanks for following us here, and see you in the next video.